Hello everyone, my name is Xiao from the Water Supply Network Department. I will be presenting on the challenge titled Internal Repair Method for Leaking Underground Potable Water Pipelines. Singapore's water supply network comprises about 6,000 kilometers of underground pipelines. Diameters range from 100 to 2,200 millimeters, with ductile iron and steel being the predominant materials. These pipelines require regular maintenance to ensure an uninterrupted supply of water. In a high-density urban environment like Singapore, such maintenance is increasingly challenging. Space is limited, traffic is heavy, and the underground is already crowded with other utilities. As a result, our current methods of addressing pipeline leaks are labor-intensive and disruptive to the public. With this in mind, I will briefly describe the current practice for repairing leaks. When a leak is discovered, the repair team first isolates and dewaters the affected section of pipeline. This step alone may disrupt water supply to the surrounding users. The team then excavates the road or ground to expose the pipe. Repairs are carried out in two main ways. External repair clamps are installed if the defect is a hole, or the leaking section of pipe is cut out and replaced if it is a crack. After repairs, the trench is backfilled and the road or ground is reinstated. This conventional approach is well established but has significant drawbacks. It is resource-intensive, costly, and time-consuming. It may also cause supply interruption and prolonged traffic disruption. In Singapore, where space is limited and underground services are congested, these challenges are even greater. These constraints highlight the need for innovative solutions that minimize excavation, shorten repair times, and reduce disruption to water supply and urban activities. We are seeking solutions that repair leaks from inside the pipeline. The preferred approach is deployment through existing access points, such as hydrants, air valves, or access manholes. Where this is not feasible, only minimal keyhole excavations may be considered. In addition to accessibility, the solution must accurately locate leaks and carry out effective repairs while maintaining both the structural integrity of the pipe and the quality of the drinking water. Equally important, repairs should be carried out with little or no water supply interruption. If a shutdown is unavoidable, it must not exceed 2 hours. I will now outline the key requirements and considerations that the solutions must meet. The solution must accurately pinpoint the location of leaks. It should also deliver a durable repair with an intended design life of ideally 50 years. In addition, it must restore the structural integrity of the pipe to withstand internal operating pressures, external ground and traffic loads, and dynamic hydraulic stresses such as water hammer. In addition to these operational requirements, the solution must also fit the context of our network. The solution should be compatible with steel and ductile iron pipes, which make up most of our network. Our priority is pipes between 100 and 300 millimeters in diameter. It would be beneficial if solutions can also be adapted for larger pipes, up to 2,200 millimeters. A commonly encountered failure mode is corrosion-induced holes, and the repair solution should be able to address these effectively. Additional capability to repair circumferential and longitudinal cracks would be an advantage. We understand that different leak types may require different repair techniques, and we welcome solutions that target specific failure modes rather than a universal approach. Finally, the solution should be suitable for straight pipe sections, while suitability at bends will be considered an added benefit. Beyond technical performance and applicability, compliance and safety are also essential. All repair materials must comply with the Singapore Standard SS375, Part 1, 2015. This standard governs the suitability of non-metallic materials and products for use in contact with water intended for human consumption. Also, the repair solution must not introduce any contaminants or affect the taste, odor, aesthetic quality, or turbidity of the water. With these requirements in mind, I will now share the expected outcomes of the pilot project. The project should aim to develop and demonstrate an internal repair method that is effective, safe, and minimally disruptive. The pilot project must be completed within 18 months. To achieve this, the solution should be deployable via existing access points, such as hydrants, air valves, or access manholes. Where this is not possible, only keyhole excavations will be considered. In terms of operation, the repair must be carried out with little or no interruption to water supply. If a shutdown is required, it must not exceed 2 hours. Beyond this, the repair must achieve a complete and durable seal that withstands typical operating conditions for at least 6 months of testing. To demonstrate this, there must be a way to monitor the repaired section during this period to confirm effectiveness and durability. In addition, the project should provide proper documentation describing how the repair was carried out and how it performed during the pilot. This will allow PUB to assess its potential for adoption. Finally, if the pilot is successful, PUB is interested to adopt the solution through a service model. For overseas providers, this would require either establishing local operations in Singapore or working with a Singapore-based partner. This concludes my presentation, and thank you for your attention. If you have any questions, please feel free to ask them in this info session.